And moving swiftly on to our next talk, we have another headliner on the topic of AI and supercomputing, the hottest new couple in tech. Our speaker is the Chief Architect for HPC and AI Business Unit at HPE, driving the convergence of supercomputing and AI from silicon to workloads at scale. He advocates for a greener IT industry and open source software with the goal of constantly enhancing and broadening the impact of leadership computing. Please give a very warm welcome to the Senior Fellow and Chief Architect at Hewlett Packard Enterprises, Nicolas Dube.
All right, thanks, Fiona. I'm really happy to be here. Very infrequently do I get to actually give a talk in Montreal. Unfortunately, I'll have to give it in English because I'd be happy to give it in French. If you guys want to talk to me in French, I don't do much business in French, but I'm super happy to be here in Montreal for the AI conference. So today I have only 100 slides for you guys. No, that's a joke. Today I'm going to talk about supercomputing and AI, and I try to come up, I was looking at getting a catchy title, the hottest new couple in tech. Why? Because a lot of people right now are struggling, and even the largest players in the industry are struggling to scale their training jobs to hundreds, thousands, multiple thousands of workloads. Well, it happens that in supercomputing, we've been doing that for quite a while. So I'll be covering a little bit how those two areas of very high tech are coming together, and why, for instance, at HPE, those are part of the same business unit. So I don't know if you know what exascale is, but exascale is a supercomputer that's able to run at 10 to the 18 calculations per second. There's only one in the world that's able to do that, and the previous speaker was mentioning it. It's clicker. Here we go. Thank you. It's called Frontier. And there might be a second one very soon. Watch the top 500 in May. I cannot break any confidential news, but there might be some shakeups at the top 500. So supercomputers are ranked every year on what we call the top 500 list. Frontier is a 25 megawatt supercomputer. It's got nearly 40,000 GPUs. 25 megawatts, so you get an idea, right? A small hydro plant that's near Quebec City, where I live, is about 17 megawatts and powers the whole east side of Quebec and the Charlevoix region. So it would not be enough to power Frontier. That's, as a computer geek, running codes on a system like that is the absolute biggest kick you can get, because when you hit return to launch a job on the whole system, the building actually shakes as the cooling system ramps up and the power transformers just start humming. At 40,000 GPUs, you can also train some very large AI networks. But the key is that it's a system that's been designed for strong scaling, not weak scaling. And I'll cover that a little bit in my talk and why it matters for AI as well. It didn't matter so much for AI before. When you were able to do image recognition or video recognition on a box of 4 or 8 GPUs, it was fine. Now that you're trying to train large language models and all of those large foundational models, and it's training or tuning, where you need hundreds or thousands of GPUs, you actually need a system architecture, and that's not just hardware. That goes all the way to the runtime. That's able to run those codes at that scale. So Frontier was my biggest baby. We've had a lot of other babies around the world. Aurora is kind of coming up right now. Same for El Capitan at Lawrence Livermore Labs. And it's all very large systems. Of course, a lot of their purpose is to advance science around climate prediction, around energy modeling. For instance, there's a lot of work happening in the US and worldwide on nuclear fusion, but also more and more now where AI gets coupled with high-performance computing and simulation to accelerate the simulation and actually get the results faster instead of really doing more like a brute force 3D physics simulation. So if you want to talk more about supercomputing, be more happy, just grab me in the hall after my talk. So does AI has become a supercomputing problem? Answer to that is pretty much yes, because if you look at the training compute intensity, the flop intensity of all of those models, the deep learning was kind of getting up there. But if you look today, the foundational models, GPT-3 and now GPT-4, that's at the very top, you're looking at more than 1 week of training on a system the size of Frontier. So now you're talking the kind of workloads we've been running on the supercomputing side for some time, and those are not trivial models to run. So now, can supercomputing fix large-scale AI issues? Now, I don't know how many of you guys are practitioners that are actually running or trying to train some large models like that, but this is some data that was collected by some of the folks running at Alibaba on the Alibaba compute clouds. On jobs that are not even that big per our reference, right, they have 128 GPUs cluster. And that's a mix of about 100 jobs, and the job length is a few hours to 24 hours. Nearly 50% of the jobs, or 43% to be precise, failed for various reasons, right? A big part of it were nickel timeouts. You have all sorts of GPU errors. You have ECC errors. And when you look at that, and you're running, whatever the platform you have, whether it's on-prem or in the cloud, you're actually paying for every GPU hour in the cloud, even on your failed runs. So what you really want to look at is how much of the GPU am I actually getting in performance. It's basically the ratio of your productive GPU hours over the paid-for GPU hours. And when you look at how uptime plays against you, and this is where the cloud and the hyperscalers, most of them are on basically by contract will give you a 99.5% uptime. The better ones will give you a 99.9. At 99.9 uptime, basically, you're going to get a job that's 10 GPUs. You're going to have about 80% completion rate. If you go below that, right, they're still within, as long as they stay within the blue or the purple area, they're still within contract. So if you're running 100 GPU jobs, right, you have basically no chance contractually to be able to execute on that. Now, in practice, the cloud's uptime are actually better than 99.9. But what I'm trying to tell you guys is that by contract, they don't have to be. And why is that so different? It's because the clouds of today have been built for mail serving, for web serving, for office applications, basically for single server workloads that can easily be swapped between one another as it's all virtualized. It's never been built for strong scaling workloads. And that's the whole difference. A weak scaling workload, you can have 10,000 servers that are all running web servers, right? One goes, you're still 99.99% up. In supercomputing, we'll be running one job on 10,000 GPUs. If one GPU goes, the whole thing goes down. You're at 0 uptime. And so it drives significant differences in how you architect the system and how you deploy it. And to the point, and that's confidential, but that pretty much all of the hyperscalers now are knocking on our door or bringing in supercomputing people to help them build the new type of cloud they need to be able to run AI at scale. What does that look like for a workload like GPT-4? As you know, GPT-4 was trained using a mixture of experts. Why? You do that because running the large-scale GPT-4 would just be too hard. But by using, if you were to use a supercomputer that would have proper resilience built in, that would be liquid-cooled, therefore more stable, that would have a high-speed file system, you'd be able to run GPT-4 in a matter of 49 days, right? But basically at a 99% efficiency. And that's what matters. You'd be having less failure, less reboots, less wasted GPU hours. So what are the next steps? I think one big takeaways I have for you guys is as you design your AI systems or as you consume your AI systems from any cloud, ask for reliable AI systems, whatever the GPU is. Needs to be liquid cooled, because now we're looking at chips that are 700, 800, 900, 1,000 watts per chip. Need to have adequate bandwidth. It doesn't have, you don't necessarily have to go full DGX with NVLink with the whole big spec, but you need more than what clouds have built typically on GPU servers. And you need a parallel file system. Why do you need a parallel file system? Because you need to be able to checkpoint your run. If you're going to run for multiple hours, if you don't checkpoint, that means that if you're failing, even just a minute before the run ends and you haven't saved state as you go, you're going to lose a whole bunch. You're going to lose pretty much the whole bunch of it. So it's all about learning these tricks. The best guys right now in the industry are doing that, but it's not something that's so pervasive just yet. Implement more granular and distributed checkpointing, right? If you're trying to hit and checkpoint all memory all at once, you're going to need a very beefy file system to be able to checkpoint that. If you're going more asynchronous, or you're more granular, you're doing smart checkpointing, you're actually checkpointing only the data you need instead of the whole memory of your GPU, you're going to be much more efficient and much faster in your checkpointing. And the last thing, and the innovation I think that needs to happen, is a lot of the frameworks today have been built using MPI and using bulk synchronous runtimes. What is a bulk synchronous runtime? It's basically what we use in high-performance computing. So think about you're doing a weather model, right? And you're going to basically have all of it. You're going to have the water model, the earth model, the air model. You're going to have inputs from satellites, from sensors, from everything. And then you're going to iterate in time steps. But at every time step, you're bulk synchronous, because you're going to do an all reduce, and you're basically going to synchronize all of your data points, and then you go the next time step. That's how simulation runs. However, that's not how the brain runs. The brains and neural networks are inherently asynchronous. But yet, the way we train large-scale neural networks today is very bulk synchronous, because that's what the frameworks that we had at hand are doing. So a really interesting area of research that I don't have enough time to cover today is to look at how we take those very large training jobs and make them run asynchronously. So then that makes you a lot more resilient to a GPU popping here and there, or basically not having to do all together, all reduce and big checkpointing. Okay, I want to finish with a more kind of a Quebec angle to this, since I'm in Montreal. I've actually used that slide at the EVE for Climate conference I was talking to last summer in Berlin, where the climate researchers were preparing for their ask for the COP, the big worldwide climate conference. So if you go to the Patterson paper that many have referenced, to train GPT-3, as you guys know, 175 billion parameters, it consumed 1,287 megawatts of electricity and generated 552 tons of carbon dioxide. Those numbers are so big that people actually have a hard time mapping that out. And then you see all of the press and all of the news about AI generating so much carbon and all that. There's actually a better way to do this. So you really want to move your training runs out of basically coal power or fossil fueled powered electrical grids. And that's something that's well known by people in the industry or in the energy industry and everything. But what's really bad is to train your neural networks on a cloud that's powered in North Carolina that's all fed by coal power. We happen here to be in a place where we have 100% renewable electrical grid. And hydro, and that's the full carbon footprint, so basically cradle to grave, so it includes the concrete that went into the dam and all of that, so that's why it has 4 grams of CO2 equivalent per kilowatt hour. So how can we use that and actually train AI in a sustainable way? I don't know if you guys heard about Qscale. Really like what these guys are doing. And they kind of woke up that this could be done in Quebec and Canada. Like, the Scandinavians were doing that almost a decade ago. But I'm really happy this is now happening in North America. And kudos to the Qscale guys. So they're building a site that will go over 100 megawatt. It's 100% renewable grid. You get free cooling year round if you're smart about it. So basically that means you shouldn't be using chillers, but basically heat exchangers with V-shaped coils. But it has, most importantly, the waste heat recapture potential. If you look at that rendering, the guys were smart and they bought the land right behind the data center, and you see those greenhouses there. Those greenhouses are going to be used to grow tomatoes, vegetables, and berries. So, how many tomatoes can ChatGPT grow? So a tip, I actually did the math for real, and I'm going to walk you guys through it. It's not that complicated. A typical 500 square meter greenhouse in Quebec basically needs 5,549 heating hours, so basically climate hours below 10 degrees C. So that's about 1,000 gigajoules per heating season. ChatGPT training at 1287 megawatt hour, that's 4,633 gigajoules, or 4.6 greenhouses of heating for 1 year. Now, what's nice about that is that greenhouses, even in Quebec, they're heated using natural gas because it's slightly cheaper than electricity. If we're heating the greenhouses by the waste heat of the supercomputer, or basically that's the key. If you're liquid cooling, because I skipped that part, sorry, I'll loop you guys back in onto that. By using liquid cooling to your supercomputer, you could cool it at 25, 30, something higher than 30 seawater coming in. But you're going to be generating the water coming out in the 40, 45 degrees C, which is plenty warm enough, that's basically heat pump warmth, to run a water glycol loop in the concrete floor of your greenhouses. So your greenhouses now are heated by waste heat that you would be otherwise throwing up into the atmosphere. So when you're doing that, now you're offsetting the natural gas heating system of the greenhouse. So if you follow that math, you're, for training once ChatGPT or GPT-3, you're saving 391 tons of CO2, or the equivalent of 85 cars of annual carbon footprint. And remember, you're running on a renewable grid. So even your electricity source coming in is not loaded with basically a lot of carbon. So this is a crazy number in the whole map, other than the supercomputer and how you use it. Believe it or not, but tomato production in a greenhouse ranges between 60 to 90 kilograms per square meter. That number threw me off. Basically, almost fell off my chair. These guys really have it ratcheted down. If you do a math that about 85% of the surface area of the greenhouse is used for production, at 4.6 greenhouses times 500 square meter times 85%, that's 1969 production square meter times 75 kilos. That's 147,000 kilograms per year. How many tomatoes is that? Anyone wants to have a guess? On the picture there is precisely a kilogram of tomatoes. You should have seen the guy at the groceries when I went there, and I had my tomatoes on the scale at the cashier. I was like, no, I need precisely 1 kilogram of tomato, and I was swapping the tomatoes in and out because I needed that picture for that slide. So yeah, it's 1 million tomatoes. So the bottom line, what I want you guys to take away today, when you want to train at scale, you need to design or purchase or consume or ask for a system that's actually able to run at scale training, something that's likely built like a supercomputer. There are ways to do it in a not only reliable, resilient, but also sustainable way, and we happen to have a way to do that in Quebec. So I hope you guys take the baton from there. Really happy to be here. Look forward to chatting some more. Thank you.